Today on Macaulay Math, we're using differentiation rules and finding rates of change. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 7 on differentiation rules. Our goals for today: we're going to find the derivative of a function using basic differentiation rules. We're going to find the derivative of sine and cosine functions, and then we're going to use the derivative to find a rate of change. The last lesson introduced the derivative, defined as a limit process. While that method is perfectly acceptable, it is rather time-consuming. This lesson begins our discussion on how we can simplify this process by using rules for differentiation. Many of these rules will be used beyond simple polynomial functions, but that's where we will start. Our first two transcendental functions, sine and cosine, will also be given rules for differentiation. Finally, we will discuss the derivative as a rate of change and introduce some of the ways in which the derivative can be applied in the real world. Let's get started. Basic rules of differentiation. For each rule, c is a constant and the functions f and g are differentiable over their domains. Number one, we have the constant rule, so the derivative of any constant with respect to any variable is always going to be 0. The simple power rule is going to say this: if you derive a monomial to a power, then the derivative of that thing will be to take that value and bring it down in front here, and then reduce the value of that power by 1. The constant multiple rule: if you have a function that's multiplied by a constant, then the derivative of that expression is going to be the constant times the derivative of the function. And then the sum and difference rule says that if you have the sum of two functions, then the derivative of that sum is just going to be the derivative of each of those two functions individually, and then you can either add or subtract them. Our first two derivatives of trig functions are going to be something that you're going to have to memorize here. The derivative of sine of x is going to be cosine of x, and then the derivative of the cosine of x is going to be the negative sine of x. Note, all the derivatives of the other trig functions can be found using these two basic derivatives. The derivative of tangent x will be proven using the quotient rule in the next section. The links for the proofs of the derivatives of all these functions can be found in the comment sections below. So the next thing we're going to do is we're going to talk about rates of change, and I have a demonstration that is going to get us started through that. So this demonstration is going to be the average rate of change, something that you've seen in pre-calculus, versus the instantaneous rate of change, which will be new to calculus. First, let's consider a ball dropped from a height of about 90 meters. I chose this height because in the real world it takes just a little more than 3 seconds for a ball to strike the ground, and it makes our numbers easy to understand. If there are no other outside forces, the ball drops linearly to the ground and maybe bounces. But if we map the height of a ball as a function of time, we get a graph that looks a little like the green parabola shown here. In pre-calculus, we are able to calculate an average velocity. Average velocity is the change in height divided by a change in time. The triangle shown here is the Greek capital letter delta, representing change as a range of values calculated through a subtraction. In this case, the ball traveled 90 meters in 3 seconds for an average velocity of 30 meters per second. Notice the units here. The numerator measures a distance, the denominator a time, so the resulting units are a velocity, meters per second. This result may be perfectly fine for the situation that you're working with, but what if we need to know more about the falling baseball? If you observe the situation, you would clearly be able to see that the ball travels more slowly when it is first dropped, then it accelerates and is moving very quickly by the time it strikes the ground. If we model the height of the ball as a function of time, then calculus allows us to do some interesting things. With a derivative, we use the notation dh over dt. We can think of this as an instantaneous change of height over the instantaneous change in time, which again gives us a velocity in meters per second. If we connect the point on this graph where the ball is released and the point where it hits the ground with a red line shown here, the slope of this secant line represents the average velocity. From the last lesson, we know that the derivative of a function can itself be a function, and in this case, it calculates slopes of tangent lines at different points. You can see here that the slope of the tangent line changes dependent upon the value of time. In this last shot, we see that times 1 second, 2 seconds, and 3 seconds, the slopes of the tangent lines are all different. And as we move from left to right, the steeper tangent lines imply greater velocities. Rates of change. The derivative is a rate of change of one variable with respect to a second variable. In physics, the Greek symbol delta represents change. Thus, the average rate of change, delta y over delta x, is the change in y over the change in x. The instantaneous rate of change is dy over dx, the rate of change of y at an instance of the value of x. So some examples. First, let's use differentiation rules to find the derivative of f. So here we're going to find the derivative of f. And so we have a few things here that we need to take into consideration. First, we have the 3x, and then also we have a difference of the 1. So we have a few rules that we're going to apply here. First, we have a constant rule when we're talking about this 1. We also have a constant multiple rule. We have the 3 in front of the x, and then we have a simple power rule because we have x to the first. So we're going to take care of all three of those things right off the bat. And so we'll say that our first derivative of f with respect to x, the derivative of this, it's going to be 3. And since this is to the first power, now we would never write a final answer x to the first power, but I'm putting it in there so we can see it. It'll be 1 times x to the 1 minus 1, and then the derivative of a constant is always going to be 0. All right. And so 1 minus 1 is 0, so I have 3 times 1x to the 0 power, and then I'm not going to write that, and anything to the 0 power is 1, so this thing is just going to be 3. So our first derivative of this expression is just going to be 3. Now remember, what does the first derivative give us? It gives us the equation for the slope of tangent lines at any given point. This original function, f of x equals 3x to the first, that is a linear equation, y equals mx plus b. Its slope is always constant. Its slope is 3, so that makes sense because this thing says that the slope of the linear function is a constant. In this case, it is 3. All right, let's move on. Again, use the differentiation rules to find the derivative of f. I'm not going to write down every single one of this particular expression, but just a couple of notes. First, there are 3 terms. I have a sum and a difference, and I have a power rule. So the derivative of this, and we can do this a couple of different ways, just so that you see the note, a little bit different notation. This notation here says I'm going to derive this expression with respect to x. So I can go dy over dx, or I could say it is y prime, either or. And so let's deal with this first term first. I have the 3 up here, so I'm going to use my simple power rule and bring my 3 down, but I have the 2 in front. So I'm going to multiply them. 3 times 2 is going to give me 6. And then I'm going to reduce this by 1 and make it a 2. I have the subtraction. The simple power rule says I bring this 2 down in front and subtract. So I'll have 2x. And now it'll be to the first. Then the derivative of 3x from the last example was just 3. And so this is my not my final answer, because clearly I wouldn't leave a 1 there for my final answer. So we'll rewrite one more time. So we have 6x squared minus 2x plus 3. That is my first derivative, dy over dx. And we'll put a box around that. And we'll move on to the next one. Use the differentiation rules to find the derivative of g. Well, we'll say g prime of t. I have a constant pi out front, so we'll leave that pi out front there. And then the derivative of cosine t, well, that's just a rule. Now, if we go back to our derivative of trig functions, the derivative of cosine x is just negative sine x. So I'll come back down here, and I will make that negative sine of t, and we should rewrite this. So we'll say that g prime is going to be negative pi sine of t, and that will be our final answer for that one. We are going to come across some functions that don't necessarily fit exactly into our simple rules that we've so far discussed. And so some things we may have to rewrite so that we can put them in a form that will allow us to use these rules of differentiation. Here is an example. I have y equals 2 over 3x squared. So I'm going to rewrite this thing as y equals, well, I'll make it 2/3, that's the fraction, and then I'll use one of the properties of exponents and rewrite this as x to the negative 2. Now I can use the simple power rule on it and say that y prime is going to be equal to, again, I'm going to take the 2, I'll bring it down in front. So negative 2 times 2/3 will be negative 4/3. It'll be x, and then again we're going to subtract. So even though it's negative, we're subtracting. So negative 2 minus 1 will give me negative 3, and we should never leave a negative exponent in our final answer. So we're going to say that y prime is equal to negative 4 over 3x to the third. Make that negative exponent positive by pushing it into the denominator, put a box around that, and say that we're done. Another example where we may have to rewrite, if I have this single monomial in the denominator, what I can do is rewrite this, and if you recall, to add fractions, you have to have a common denominator. So a over c plus b over c is equal to a plus b all over c. Well, if this is a rule, if I go from left to right, I should also be able to go from right to left. So here I have a sum of two different terms all over c, and then I can separate that into two fractions that are being added. So I'm going to rewrite this and say h, and again, I'm only writing as h because I haven't done the derivative yet. I'm going to rewrite this as 2x squared over x minus 3x over x minus 1 over x. And now I'm going to simplify. And I'm again going to leave it as h. So this will become 2x minus 3 minus x to the negative first. Now I'm going to derive. And we'll say h prime of x is going to equal to, well, the derivative of 2x, just like in the first example when we took the derivative of 3x, we just got the constant 2. The derivative of any constant is 0. And just like in the last example, we bring that negative down. So negative times negative 1 will be positive x. And then I reduce this negative 1 by 1, that'll give me a negative 2. And now I'm going to simplify. And we will rewrite this as 2 plus 1 over x squared. Now this is perfectly acceptable answer as is, but you could also rewrite this as a single fraction if you so desired, and rewrite that as h prime of x. I would use a funky 1 to get a common denominator and rewrite this as 2x squared plus 1 all over x squared. That is also perfectly acceptable. Next example, the position function for falling objects is h of t equals negative 16t squared plus v sub 0 t plus h sub 0, where h is the height, t is the time in seconds, v sub 0 is the initial velocity, and h sub 0 is the initial height. And this is going to be in feet in seconds. If a ball is dropped from a height of 1,000 feet, find h prime of 2, and using the appropriate units, describe what this value means in the context of the problem. Okay, so let's start with our equation. H of t equals negative 16t squared plus v sub 0 t plus h sub 0. So we're going to substitute our given values. Now we know v sub 0 is equal to 0 because the ball is dropped. We know that h sub 0 is 1,000 because that is my initial height. Now because v sub 0 is 0, we can just cancel this out and rewrite this h of t as negative 16t squared plus 1,000. Now they want us to figure out what h prime of 2 is. Okay. So the first thing I'm going to do is I'm going to derive with respect to time. So that is technically, and again, we could write it as h prime of t, but we can also write this as dh over dt. And that will give me, and I'll do the derivative, so I bring the 2 down. So 2 times negative 16 is negative 32. And then reduce the 2 by 1, so that'll give me t to the first. All right, so this is my derivative, and then they want me to say what is h prime of 2. Well, that'll be negative 32 times 2, which will be negative 64. So that is my value, and my units, dh over dt, will be the change in feet per second. So this thing is negative 64 feet per second. And so to describe what this means in the context of the problem, after falling for 2 seconds, the ball is traveling towards the ground, hence the negative 64, at a rate of 64 feet per second. All right. Well, folks, that's all I got for today. So, the Star Wars fun fact of the day. The Tatooine scenes from Star Wars A New Hope were filmed in Tunisia, and the production company built a large mock-up of the Jawa sandcrawler, which I have shown in this picture here, which almost caused a war with neighboring country Libya, whose ruthless dictator, Muammar Gaddafi, believed that the set piece was a military vehicle, even though it was just a prop. That's all I got for today, folks. Have a good day. Goodbye.